The ecological niche is an important component to understanding the formation of ecological communities, including how they are structured, which species are present and why, as well as how patterns of diversity take shape. These are not only necessary for our understanding of the natural world, but also, in an applied sense, this level of understanding is critical for predicting the outcomes of environmental change, from small-scale land use change to global climate change, as well as the development of conservation plans that maintain ecosystem services and prevent species extinction. Despite its prevalence, the niche has been a confusing and, at times, controversial topic in ecology. Even today, there is no one universally accepted definition. With this in mind, we'll take a look at one of the classic descriptions, Hutchinson's fundamental niche. I'll go over a little of the history leading up to the development of the fundamental niche, and I'll briefly mention some of the important contributions that followed. This being such a broad and important topic, I'm hopeful that this will be the first in a series of videos. Let's begin with what most ecologists consider to be the foundation of the niche concept, and that would be with Joseph Grinnell. While the ideas underpinning the niche, as well as the term itself, both predate Grinnell, he is generally credited with framing the concept, something that is apparent in his 1917 publication on the California thrasher. In that paper, he used terms such as the role of a species, or its place in an ecological community. In this sense, Grinnell is putting emphasis on the environmental components that determine a species' distribution, to the point where the niche is seen as a set of environmental conditions that exist regardless of whether or not a species is present. So the niche, in this sense, is a property of the habitat. Here, niches exist in the environment, and organisms evolve to fill them and to exclude other species from impeding on them. From Grinnell, the next logical step is to Charles Elton. Elton's contribution was to shift the focus much more towards species. Specifically, Elton was focused on predator-prey interactions and the trophic structure of ecological communities. Here, a species' niche is a functional role in a community and is primarily explained by their trophic position. Elton presented several examples. You've probably heard of the tawny owl and the kestrel as one. However, he also talked about the Arctic fox, which feeds on the eggs of Arctic birds in spring and summer, and scavenges on seal carcasses left by polar bears in the winter. He compared this to the functional role of a hyena in the African plains, which feeds on birds' eggs in one season and scavenge from lion kills in other times. There is, of course, much more to say about both Grinnell and Elton. We've really just glossed over them here. But it sets the stage for the focus of today's video, G. Evelyn Hutchinson. Like Elton, Hutchinson also thought of the niche as a property of species. However, his focus was at the population level. In his landmark 1957 address to the Cold Spring Harbor Symposium, he laid out a quantitative description of the ecological niche, which he saw as the range of environmental conditions that allow a population to persist. This led to its other common name as the population persistence niche. When Hutchinson says persist, he's referring to the ability of a population to either maintain or increase the number of individuals. For example, if we take a simple population growth model, such as the exponential growth equation seen here, where the change in the number of individuals over time is a function of the number of individuals and of little r, the intrinsic rate of increase. For a population to persist, this value would need to be either 0 or positive. If R was negative, the population would decline to extinction. I mentioned his concluding remarks address to the Cold Spring Harbor Symposium, so let's turn to that paper and see what Hutchinson says. Consider two independent environmental variables, x1 and x2, which can be measured. Let the limiting values permitting a species S1 to survive and reproduce be respectively x'1, x'1 for x1, and x'2 and x'2 for x2. Let's take a moment here and break down what he means, starting with these variables. So what did he mean when he said x1 and x2? As mentioned, these can be any two independent environmental variables. Independent meaning the value of one is not dependent upon the value of another. Let's pick something here and see how this plays out. Let's start with temperature, and we'll use that as our x1. We can have a range of temperature, and we'll place that along an x-axis. Now, it says, let the limiting values permitting species S1 to survive and reproduce be x'1 and x'1. So, species S1 has some range of temperature within which it can persist. Let's add those into the graph. There will be one lower thermal limit, we'll call that x'1, and some upper thermal limit, we'll label that x'1. Within these thermal extremes, the ability of species S1 to survive and reproduce will vary. So let's add that in. For convenience, let's just label the y-axis as fitness. Okay, wait, hold on. Let's pause here because there's a problem. Take a look at that y-axis, fitness. Remember, we're talking about populations here. Fitness is a characteristic of individuals. Indeed, the variation in fitness among individuals in a population is one of the key components of natural selection. Selection occurs at the level of the individual. Evolution occurs in populations. Therefore, populations don't have fitness. So to make this work, we would need to use something like average fitness of individuals across populations. Using averages introduces some estimate error, so we just need to be mindful of that when making conclusions. Of course, there are other options. For example, that R value mentioned earlier, the intrinsic rate of increase. Well, R is sort of like a population level proxy for fitness, since it flows directly from the birth and death rates of the population. But let's go with average fitness. And this looks good. So now let's do the same thing for another variable, x2. Pick your favorite environmental variable. I'm going to say let's use rainfall as our x2. And be sure to note the limiting values x'2 and x'2. Now let's put these together and see what it looks like. Here we have a two-dimensional area indicating the values of temperature and rainfall that permit species S1 to survive and reproduce, with the shading indicating that variation in average fitness. To quote Hutchinson, an area is thus defined, each point of which corresponds to a possible environmental state permitting each species to exist indefinitely. Now, I want to clarify that I'm not sure if Hutchinson was really concerned with the variation in a species' ability to thrive. For example, at points near the thresholds, species may be just hanging on, while in more favorable conditions, they may be increasing in population. If we look at the figure Hutchinson used in his writing, it doesn't seem like it. It seems as though he was only concerned with persistence as a yes-no binary kind of response. So this is my interpretation, and I'm going to keep going with it. Next, Hutchinson tells us we may now introduce another variable, x3. So let's just take what we've done and we'll add in a third dimension, basically a z-axis. Here, I'm going to say we use prey size as our x3. Like the others, it will have some upper and lower limits that correspond to the tolerances of species S1. And with this, we now have a volume and a shaded three-dimensional, in this case, sphere-like form. It doesn't have to take this specific form. From here, we could continue adding in additional dimensions corresponding to additional environmental variables, though we're going to run into problems trying to illustrate this. I suppose you could use a tesseract for the fourth dimension, but anyway, I think you get the point. Let's see what Hutchinson has to say about adding in more and more variables. In this way, an n-dimensional hypervolume is defined, every point of which would permit the species S1 to exist indefinitely. For any species S1, this hypervolume, N1, will be called the fundamental niche of S1. So now we see where that famous term n-dimensional hypervolume comes from, and hopefully we have a good understanding of what it means. If you're thinking, wait a minute, this doesn't include any competitive interactions. Well, you're right. And Hutchinson recognized this and dedicated a separate term, the realized niche, to describe that portion of the fundamental niche that a species actually occupies after accounting for competitive interactions with other species. So we might think of the fundamental niche as the potential and the realized niche as the actual. In this regard, the realized niche is smaller than the fundamental. While Hutchinson's work was groundbreaking, it is not without issue. For example, he so precisely defined the niche so as to be almost impossible to actually determine for any species. How many dimensions do we need to measure to get a good estimate of a species' fundamental niche? And how difficult is that going to be? Imagine raising a bunch of individuals of a species at different temperatures, different rainfall amounts, different prey sizes, and on, to determine how each variable affects fitness. So, as important as Hutchinson's work was, and as influential as it remains today, it continues to be refined as the discipline of ecology moves towards a modern niche concept. In the 1960s, ecologists, including Robert MacArthur, a former student of Hutchinson's, along with Richard Levins, revised his concept to focus on resource utilization. This allowed for more than one species to utilize the same resource as long as it was being accessed differently. And this helped to explain the high diversity seen in most ecosystems. The 1980s and the 90s were a turbulent time for the niche concept, but also an exciting time, as new work on the factors that structure ecological communities came to light. In the early 2000s, two highly influential books were introduced, which both approached species interactions and the ecological niche in a very different way. One was Hubble's neutral theory of ecology. The other was Chase and Liebhold's ecological niches. Between Grinnell and Hutchinson to Chase and Liebhold, and the more than 20 years since the publication of that book, many other significant works have been published. As mentioned at the outset, the niche is central to understanding the assembly of ecological communities, predicting responses to environmental change, and the development of conservation strategies. Clearly, there's much more to look forward to with this topic. But that's all for now. See you next time.